You are falling toward a black hole again. This time, you are not planning to orbit or turn away. You are on a trajectory that will carry you across the event horizon. From far away, the horizon is defined in a simple way. It is the surface beyond which not even light can escape. Inside that boundary, every possible path you could take leads inward, deeper toward the center. Outside the horizon, you can still fire your engines, change your course, and climb away if you have enough power. Inside, no amount of thrust, no clever maneuver, no future technology can get you back out. This is not because you are trapped inside a wall or a physical shell. It is because the geometry of space-time itself has changed. Near the horizon, light paths bend inward. The cones that represent possible future directions for light and matter tip more and more toward the center. At the horizon, those light cones tip so far that all future paths point inward. From your point of view, falling freely toward the black hole, nothing special seems to happen exactly at the horizon. Your ship does not hit a wall. There is no sudden jolt, no bright flash, no obvious boundary you can see or touch. The horizon is not marked by a sign that says, "You are now entering the inside." It is a surface defined by where light goes, not by what your hands can feel. But from the perspective of a distant observer watching your fall, the story looks very different. As you approach the horizon, your signals climb out of a deeper and deeper gravitational well. They become weaker, more red-shifted, and more delayed. To that distant observer, it looks as though your fall slows down, stretching toward a halt right at the horizon. They never see you cross it. Your last image seems to freeze, fade, and slide toward red. Both stories are predicted by the same theory. Relativity allows your own experience and the distant view to disagree on what happens and when. For you, there is no mystery. You keep falling. For the outside universe, you seem to hover forever at the edge. The event horizon is where these two descriptions pull apart, and where our intuition about inside and outside starts to break. Let us follow your experience, the one falling in. You cross the horizon without feeling a bump. The black circle ahead of you still fills more and more of your view. Behind you, the outside universe is compressed into a shrinking patch of sky. Inside the horizon, the roles of space and time change in a subtle but profound way. Outside, you could decide to move closer to the black hole or farther away, just as you can choose to move north or south on Earth. Inside, moving radially inward is no longer a choice. It becomes more like moving from one moment of time to the next. In Einstein's equations, the coordinate that measured distance to the center takes on a time-like role. Your future, in the mathematical sense, leads inevitably to smaller and smaller radii. There are no stable orbits here, no safe paths that circle around without falling in. All free-fall trajectories inside the horizon end at the same place, the singularity at the center. From your point of view, this does not feel like being forced along a track. You still feel weightless in free fall, at least for a while. Objects you release float beside you. Light you shine still moves outward, but its paths curve back inward more and more tightly. If the black hole is supermassive, tidal forces at the horizon might be gentle. You could cross it without being torn apart immediately. Only as you fall deeper toward the center do those tidal forces grow, eventually crushing and stretching you as in the previous episode. If the black hole is small, you may never live to see the inside. the zone where spaghettification becomes lethal, can lie outside the horizon. In that case, your journey ends before your body ever reaches the boundary that mathematicians call inside. But if you could survive the crossing, relativity gives a clear answer. You would experience a finite amount of time, a few seconds or minutes or hours, depending on the black hole, before hitting the center. From your own perspective, the inside is real. You do not freeze at the edge. You fall, and your story continues for a while until space-time runs out. So far, we have trusted Einstein's theory of general relativity. It has guided us through orbits, horizons, and fall times, and it has matched every test we have been able to perform in the universe outside. But at the very center of a black hole, that theory predicts something disturbing. It says that space-time curvature grows without bound, that densities and tidal forces become infinite. At that point, the equations themselves cease to make sense. The paths of particles cannot be extended in any meaningful way. We call this a singularity. In the language of mathematical physics, it is a sign that the theory is incomplete. We do not believe that nature actually produces a point of infinite density and zero volume. We believe instead that our description breaks down before we get there. At extremely small scales, quantum mechanics must enter the story. Space and time may no longer be smooth and continuous. They may have a granular, probabilistic structure governed by a theory of quantum gravity that we do not yet possess. We already know that when we combine quantum mechanics with the curved space-time around a black hole, strange things happen. Black holes are predicted to radiate through a process known as Hawking radiation. Over immense timescales, they can slowly lose mass and evaporate away. This leads to deep puzzles about what happens to information that falls in. Does it disappear? Is it somehow encoded in the radiation? Does the interior we have been imagining even exist in the way we think it does once quantum effects are fully taken into account? Physicists have proposed bold ideas. That the horizon might be surrounded by a firewall of high-energy quanta. That space-time inside could be connected to other regions by wormholes. Or that information is stored holographically on the horizon itself. These are active research topics, not settled answers. What they have in common is an acknowledgement that our classical picture of the inside cannot be the whole story. Near and beyond the horizon, general relativity and quantum theory collide, and we do not yet know exactly how to make them agree. So, does it make sense to talk about the inside of a black hole at all? From your perspective, falling in, the answer is yes. You cross the horizon. You feel time pass. Events happen to you in a definite order. You see the universe above you compressed and distorted into a shrinking patch of sky. Your story continues until you reach the region where our equations fail. From the perspective of the outside universe, the answer is more subtle. No signal from your experience on the inside can ever reach them. For them, the horizon is a boundary not just in space, but in knowledge. Everything they can test, measure, and confirm about the black hole comes from its exterior. Its mass, its spin, its charge, its influence on nearby stars and gas, and perhaps its Hawking radiation. The interior remains hidden, not just behind darkness, but behind the limits of what signals can carry. In that sense, black holes are like mirrors held up to our theories. They force us to ask which parts of our descriptions reflect something real about nature, and which parts are artifacts of the tools we are using. Is the singularity a place that exists, or a label for where our map stops working? Is the inside a region of spacetime with physical events, or a convenient construction that will be replaced by a deeper quantum picture? Right now, we do not know. What we do know is that black holes, their horizons, their radiation, their extremes, are our best laboratories for testing ideas about space, time, and information itself. From far away, a black hole looks simple and silent, defined by just a few numbers. Up close, and especially inside, it becomes a place where our most successful theories go to their limits. To understand what truly happens there is to understand whether space and time are fundamental or just the surface of something deeper. And until we have that deeper theory, the inside of a black hole will remain one of the strangest, most mysterious regions our minds can visit, even if our bodies never can.